this video we will discuss case number 4. So here case number 4 is refraction from denser to rarer medium for concave spherical surface. So this time the refraction is taking place from denser to rarer medium, okay, but in the earlier 3 cases that we discussed, there the refraction was taking place from rarer to denser medium. So this time the object will be placed in denser medium, okay, and the shape is a concave shape. As I already told you that we look at this shape always from the rarer medium. So the rarer medium is this side. So from this side, if you look at the surface looks like a concave surface. So that is why the shape is a concave one. And now the object we placed in the denser medium, this side is what? Denser medium. The refractive index of this side is mu2, the refractive index of this side is mu1. That one you can write down, okay, mu2 and mu1. Then here the object is placed here, okay. The normal, as we know that normal means always the line should be drawn from the center of curvature. So since the curvature is like this, if you make a complete sphere, then this is the sphere, this will be the center of the sphere. So this is the radius center of curvature. From the center of curvature, draw one dotted line at point A like this. So this will be the normal, okay. Now if this is the normal, this is the incident light. So this incident light, it is moving from denser to rarer medium, so it will go away from the normal, okay. So that is why the refracted light, it bends like this, okay. Now if it bends in this direction, what we know that this is the refracted ray and this is the normal, so this will be the angle of refraction and this will be the angle of incidence. Now apart from angle of incidence and angle of refraction, we have 3 more angles. That is the incident rays making an angle alpha, I mean from object with object, then with image beta, with C it is gamma. And another thing that you will do is, this is the principal axis and this principal axis, along the principal axis we also consider a light ray, so here you put one arrow, okay. Then this light ray and the light ray which is towards the principal axis, they will never meet in right hand side direction. In this direction they will never meet. So what we will do is, you have to extend it in backward direction so that it meets the principal axis at point I, and the point I will be the virtual image, okay, virtual image, because both the light rays, they are not actually meeting, but we are extending it to meet, okay. So virtual image. Now the process is same how we did the earlier derivations. We started with Snell's law, so this is Snell's law, but yes, this time the law is like this: sin I by sin r. If you remember, in the first derivation already I told you that this value, it was equal to mu2 by mu1, because light ray was moving from rarer to denser medium, from mu1 medium to mu2 medium. But in this case, light is moving from denser medium to rarer medium, means mu2 to mu1. So this thing will be mu1 by mu2, okay. So that means here we have mu1 by mu2. If it is so, you do the cross multiplication, what it should be? It will be mu2 sin I equals to mu1 sin r, okay. So there is the change. Then the same steps again. Sin I and I both are same, so sin I can be replaced by I. Sin r and r both are same for small angles, so sin r can be replaced by r. So this becomes equation number 1. Next step, what we do? 2 triangles we consider. As I told you, the name of the triangles will be always same. And remember that this point where all the light ray meets the surface, we name it as A. Then the normal which is dropped, the normal intersect the principal axis at point M, and P is the pole. So the names always you keep same, so that you can consider triangles with same name, okay. So in OAC, you see that OAC, in this triangle, which one is the exterior angle? I is the exterior angle, so I will be equal to alpha plus gamma, interior angle alpha and gamma. So I equals to alpha plus gamma. Similarly, another triangle IAC. So if you consider IAC, that is IAC, in this the exterior angle is R and interior angles are gamma and beta. So R equals to gamma plus beta. This is given equation number 3. Now substitute the values of R and I from equation 2 and 3 to equation 1, just as we did in the earlier cases. So this is equal to, we get this value. Okay, now alpha, beta, gamma, these are small angles, so these angles can be replaced by 10 alpha, 10 gamma, like 10 beta and 10 gamma, like this, because just we know this one. Okay, this is a little mistake here. This will not be sin theta, you make it 10 theta for small angles, just as you did in the previous cases. In previous cases you wrote 10 theta, so by mistake I wrote sin theta, you make it 10 theta. For small angles 10 theta is equal to theta. Okay, now 10 alpha, what do we do? 10 alpha, go to the diagram, look at the diagram. 10 alpha means it is perpendicular by base, so perpendicular is AM, base is what? OM. You just see the diagram, like in the same way, gamma means AM by MC, then beta means AM by IM, gamma means again AM by MC. Now from this AM will get cancelled, all the AM, so we get these things, and this M is replaced by P in all the cases. The reason is that M and P are very close to each other, as we did in the previous cases. Okay, then the sign convention. So OP means object, the object is kept in which side? Towards left, so minus U. PC means radius of curvature, the radius of curvature is towards right according to the diagram, so R is positive. IP is the image distance is image and object both are in the same direction, it is virtual, right? So V is also minus, so minus V, R is plus. Now you change the sides. How we will change the side? The terms containing R, this one and this one, will take it in one side, rest term will keep it in other side. So now see, the equation has changed. It is not like the previous one, because in the previous three cases refraction was taking place from rarer to denser medium, but in this case it is from denser to rarer medium, so there is a change. In previous case it was mu 2 by V minus mu 1 by U, but here it is mu 1 by V minus mu 2 by U, and in previous case it was mu 2 minus mu 1, but here it is mu 1 minus mu 2. Okay, so this is the equation. Now case number 5. Case number 5 also I have given you the diagram. You do the derivation just like this, same process. Okay, just like this you do, and you will get the same equation, because here also the refraction is taking place from denser to rarer medium. Okay, and for convex spherical surface generally we get real image as well as virtual image, but real image one is here, that is case number 5. Case number 6, if you can see it from any reference books, otherwise these 5 cases are more important. Okay, so this is the diagram for a real image formed by convex spherical surface. So I think you will be able to do this derivation. Remember, your result will be this one, not the previous formula. Okay, refraction is taking place from denser to rarer, that's why. Okay, then we will use this formula to derive one formula that is called Lensmaker's formula. So in next video we will discuss about Lensmaker's formula. Thank you.